Welcome to the second lecture of logic. Today we will generalize the language of propositional logic that we have seen last week. Last week we considered only formulas in the so-called conjunctive normal form, and today we will introduce the full language of propositional logic. This means we will again talk about syntax and semantics, and then also how to use it in a practical context. As a motivation, let's look again at the example we have already discussed last week, where we want to plan a party and where we get some constraints in order to have a consistent guest list. So first constraint was that we invite couples either in such a way that both come or none of them come. So if two people are married, both partners come or none of them comes. Then we know that Alice is married to Bob and Cecile is married to David. We invite, then if we invite Alice, we also have to invite Cecile, but Cecile does not care if we invite Alice. David and Eve can't stand each other, so it's not possible to invite both. And we want to invite Bob and Fred for sure. How can we find a guest list, or is there any guest list? This is the question. And we can encode this problem into propositional logic. We introduce propositional variables that reflect whom we invite. So if we have, for example, this propositional variable invite Alice, then this variable should be true if we invite Alice. And same for the other propositional variables. These are propositional variables as we have seen them in the last lecture. And now we want to connect those variables such that the constraints that we have seen on the previous slides are expressed. And for this purpose, we now use different connectives than just these we had in the last week, which were disjunction, conjunction, and negation, and they were used only in a very specific order. And now we want to have a language which provides us more freedom. And to say that invite Alice and invite Bob should always have the same value, we use this equivalence operator then to express that if we invite Alice, then we also have to invite Cecile. We use implication. So invite Alice implies invite Cecile. Then if we want an exclusive OR, we simply negate this equivalence, meaning that only one of these variables can be true. And in order to state that we invite Bob and invite Fred, we just use the variables that we have for this context and or that we were introduced in order to express this knowledge, and just combine this conjunctively. And now we have all the constraints, and this we put into a big conjunction and get the formula we have here. And in the following, we will now have a look how we build formulas with the symbols here. We have to agree on some syntactical rules, and then we give it also a semantics. Okay, first let's say how formulas of propositional logic should look like. And for this purpose, we define the set of well-formed propositional formulas, so those formulas which are syntactically okay. And this is the smallest set that contains, first of all, the truth constants, bottom and top. This we have already seen. Then it contains all the propositional variables of interest. For this purpose, we define a set of propositions which are of interest, and all these variables are included. Okay, this is nothing new. And now, if we have a formula in our language, then also the negation of the formula is in the language. Yeah? So we can take any formula and simply put a negation symbol in front of it. And if we have two formulas in our language, then we can combine them with one of these connectives we have here. We have the disjunction, the conjunction, the equivalence symbol and the implication. And if we connect two formulas, we build a new formula, which is again in the language of propositional logic. And we call the elements of this language of propositional logic propositional formulas. And now we do not have this restriction anymore that a formula is a conjunction of clauses where a clause also has a certain structure, but now we can nest the different connectives arbitrarily, and in addition we have also more symbols. And very important, negation may occur in front of arbitrary formulas and not only in front of variables or truth constants. Yeah, now with these more complicated formulas, we also have to be a bit more careful about putting parentheses at the right position, and in particular it's important to agree on some rules of precedence. So we have to know how things have to be put together if there are no parentheses. For example, when you think about very simple expressions with multiplication and addition, then you always say that the multiplication binds stronger than the addition. Yeah? And some similar conventions we have here for our logic. Negation binds stronger than the conjunction. Conjunction binds stronger than the disjunction. The disjunction is stronger than the implication, and the implication is stronger than the equivalence. Yeah? And in consequence, we can write down a formula like we have it here without any parentheses. And these rules we just stated then say how we have to put things together in order to have a unique representation. Yeah, and let's consider this example here. The negation binds strongest, so it belongs to the A, so we can put in parentheses around the not A. Then here we have the and symbol, here we have an or symbol, then the and binds stronger as the disjunction, therefore not A and B belong together. And then we have here the disjunction, implication, equivalence, and if we also here consider this rule of precedence, we get the formula here. And in a similar case, we have two more examples that illustrate how these rules of precedence enforce us to put parentheses around formula parts, or it tells us how to read the formula. Important, since we have binary operators, we assume them to be left parenthesized, so we assume them to be left associative, so to say. And where do we have an example for that? Here we have a prime or a double prime or a prime again and something. Yeah, the and binds definitely stronger than the disjunction. But now we have two disjunctions next to each other, and since we agree to have we have precedence on the left, we put parentheses around a prime or a double prime. Yeah? When you recall the properties we introduced last week, then in fact it does not matter in the case of conjunction and disjunction where to put the parentheses, and in fact we will interpret these also as not as binary operators but as n-ary operators. Okay, but this is a bit complicated to grasp how to put parentheses around it, and as you have seen, it's not so straightforward when we read the formula from left to right, how things belong together. And for this purpose, we now introduce formula trees. But before we can do so, we have to introduce the notion of trees. And what we introduce is in particular a rooted tree. And a rooted tree is a special kind of graph which has the following properties. So every single vertex, or a single vertex, is a tree. Yeah? So if we have a graph consisting of just one node, this is a tree. And we call this vertex the root of the tree. Okay, so this is the very basic case. We have one node, and this is the root of this very simple tree. If we now have n trees, yeah, t1 to tn, and each of them has a root, so t1 has root v1 and tn has root vn, we can combine them to a new tree. Let's take a fresh vertex, yeah, which does not occur in any other tree, and then we make this fresh vertex the root of the tree, and we add edges from this new node to the roots of these small trees we have seen before. And the vertices which were previously the roots of these smaller trees are now called the children of V, because they're directly connected. Yeah, and this is how we can define a tree. More details on trees and graphs you will get in discrete structures in case you're studying computer science or in the math class. But for us, this very simple basic definition is enough. And yeah, let's have a look at an example. Here I have drawn two trees. The first tree consists only of one node, which is the root, and this root node is called V. And here in the second tree I have three nodes. The root node is A, and it has two children, B and C. And important, if a node does not have any child nodes, then it's called a leaf. Okay, and if we introduce another node, say X, then we can build a larger tree by connecting X to V and X to A, and then this node X is then the root node of this new tree. And we will use now trees to define and describe the structure of formulas. A tree that represents a formula has as inner nodes the connectives and as leaves the truth constants and the variables. And usually the nodes that are labeled with a negation symbol have one child, and the nodes that are labeled with any other connective have two children. For case of simplification, we sometimes interpret the disjunction and the conjunction as an n-ary connective or as an n-ary operator, and if we do this in the following situation, if we have a node n and a child node c, which are of the same kind, either a conjunction or a disjunction, then we can merge them, and the children of C become the direct children of N, and we remove C. We will see in an example what this exactly means. And important, usually the order of the operands does not matter. They are commutative. The only exceptions in the operators we usually use is the implication, where it makes a difference what is the first operator, what is the first operand and what is the second one, as we will see in the semantics. So we therefore make the convention that we assume that there is an order. I do not introduce this formally, but we say we read it from left to right, because if I would introduce it formally, then the definition of the tree would become more complicated, and we just can also agree upon the fact that implication has an order. Okay, and important is that the tree structure reflects the use of parentheses, so we have a unique data structure in order to represent a formula, and this is then very easy to process and also very easy to evaluate. Now let's look at an example. We have this huge formula here, and in the first step, in order to obtain the tree, we just write down the variables and the truth constants these are the leaves of the tree, and then we connect them respectively. So here we have the C. The C is preceded by negation symbol, so we get not C as a tree. And then we have B or not C, so we connect the node B and this not C with a disjunction. And the same we do for the disjunction here, and we get A or, and this formula here, and so on. And with this we can establish the full formula. And if we look here, we have an OR here, a disjunction here, and also here in this node we have as a child node a disjunction. What we can do now is we can merge the two, same situation here, and then when we merge this, we become here a disjunction which has now 3 child nodes, A or B or not C. This is here. And this is not a problem because of the property of disjunction, like the property of commutativity and also associativity. Yeah, so it doesn't matter how we put the parentheses, and therefore we can also put it here. And again, for the implication, it's important that we agree upon the order. For the other, it doesn't matter. Because of commutativity, A implies not B is meant by this tree here, and not B implies A. Yeah, so we really have to read it from left to right. Otherwise, it would be different. But yeah, for sake of simplicity, we just use our convention here. Okay, and then we are almost done with the syntax. Just the notion of subformula, which is rather straightforward to define when we have the formula tree of a formula. First of all, let us say what is this immediate subformula. A truth constant and an atom do not have an immediate subformula. Yeah? So they cannot be further disassembled. And if we have a formula not phi, then this has exactly one immediate subformula, and this is phi. So if we have not phi, the immediate subformula is phi. And if we have a formula phi circle psi, where cycle stands for conjunction, disjunction, equivalence, or implication, then this formula phi circle psi has two immediate subformulas, phi and psi. And informally, we can understand the subformula as a formula that is part of a formula. And now we're interested in all the subformulas of a formula, and this is the smallest set such that the formula itself is in this set, so phi is in this set, and if psi is in this set, then all immediate subformulas are in the set of subformulas. Okay, and now we can have a look here at this example. So the formula itself is in a set of subformulas, which we have here, and then the immediate, so that we have to identify the topmost symbol. When we construct a tree, we would look at the root, and this is the implication. So the immediate subformulas of this big formula here is A or B. So A or B is in the set of subformulas, and this C and not D is a subformula. This we have here, and then we further disassemble it and get finally the set of all the subformulas. Yeah, we have not D, we have not D, we have D, and we have A by C. Yeah, that's it. Okay, and in order to get such a formula into the solver, we have to define how a formula, for example, for Limbo has to look like in order to make it processable with Limbo. And for this purpose, we can define this grammar here. And this grammar says, in principle, which symbols are allowed and how these are connected. And what we get is we get the rule. This grammar also describes the rules of precedence. Yeah. So here in the what we have here is, I do not want to explain this too much into detail, but this is a very common concept in computer science to describe a language, and we have terminal symbols and non-terminal symbols. Terminal symbols are here under this quotation, and this means that they are not further expanded. And then we have the non-terminal symbols, which are here in these brackets, angle brackets, and they are further defined, and then they are basically substituted, yeah. And the expression, this is the thing what we want to define, is an if and only if statement, so an equivalence. An equivalence is either an implication, and this pipe here, this is a symbol of the description language for the structure, is so we have either an implication or we have an equivalence here, and on the left side is implies, or on the right side is an implies, and then we have the definition of an implies. This is an or it's a formula with a topmost symbol or implies another formula with a topmost symbol or, and we have the implication in both directions, so from left to right or from right to left. We can use both. Then we have the or, which is notated by a pipe symbol. We have the and, which is notated by this ampersand. We have exclamation mark, which is the not, and we have parentheses. And we, as a basic element, we have the variables, which is a string over letters, digits, and some special symbols. Yeah, and this looks a bit complicated, but it exactly defines the rules of precedence we have introduced before. And if we want to express this formula here, for example, in Limbo, then we simply can type A, pipe B, which is this A or B, implies this by a minus and a greater than symbol, and then we have C and not D, put this in parentheses. Yeah, later on we will see another example. But with this we are done with the syntax and come to the more interesting part of the semantics. Semantics is also a generalization of the semantics we have seen for the CNF formulas. And first of all, we introduce the notion of assignment. And this we need in order to give a value to the variables. And a variable can take one of two values from the two-value domain B, the Boolean domain, which contains elements true and false. True we write as a 1 and false we write as a 0. And an assignment is simply a mapping from the propositional variables to the Boolean domain. And as last time, we sometimes write an assignment as a set of literals, and if a positive literal is included in the set, then we set the respective variable to true. If the negative literal is included in the set, we set the respective variable to false. And also, no surprise here, if we have n variables, then 2 to the power of n assignments are possible. And now we need to define the meaning of the different operations. This is now a bit more work as with the restricted structure in the CNF. For the negation operator, we have a unary connective with exactly one element, and we can also have a different notation for the not operator. Yeah, we can use the exclamation mark as in Limbo, we can write an overbar, we can write a minus, or we can simply write not. It might also be other notations as well. We use the classical logic notation, yeah, and we can define the meaning of the negation in terms of a truth table. If a formula phi is false, then not phi is true. If a formula is phi is true, then not phi is false. We can also show this how it looks in terms of this diagram here. We have here in the rectangle all possible assignments. In the circle are those assignments that make phi true. We have psi here as well. We do not need it for the negation because we have only one argument. So we need only phi. And those assignments which makes not phi true are those which are here in the green area. and these are those under which phi evaluates to false. Yeah, here I have an example. If the atom it rains is true, then the negation it does not rain is false. If atom A is true, then not A is false. If formula A or X and Y is true, then the negation of this formula is false, and so on. Yeah, so negation inverts the value of a formula. For the conjunction, we have it as before. If both subformulas, if both immediate subformulas are true, then their conjunction is true, and this means in this set view that the assignments that satisfy the conjunction of two formulas are in their intersection of those assignments which satisfy phi and which satisfy psi. Yeah? And as before, we can use this big conjunction in order to abbreviate the conjunction of n formulas, and also here we can have different notations to write down an end. Yeah, and some important cases, A and not A is always false, because one of the immediate subformulas is false. Top and A is true if A is true, and bottom and phi is always false, because bottom is always false. If A or B is true and not C or D is true, then A or B and not C or D is true under a certain assignment. Yeah? This junction works dually. It's true if and only if at least one of the arguments of the disjunction is true. This is also reflected here in the truth table. When we look at the set view, then at least one assignment has to make one of the two immediate subformulas true in order to make the disjunction true. Some examples: A or not A is always true. Top or A is always true, because top is always true. Bottom or A is true if A is true, so this depends on the value of A. If A implies B is true and not C implies D is true, then A implies B or not C implies D is also true under a certain assignment. Then the implication. An implication is true if and only if the first argument is false, or if both arguments are true. So ex falsum quod libet is classical characterization. If this phi here is false, then it doesn't matter what value the psi has, the implication is true. Only if phi is true and psi is false, then the implication is true. Yeah, you can imagine this is a if then else, which is a Boolean expression, and it says if phi then psi. Yeah, so if and this statement is only true if psi is true and then psi is true, because if phi then psi has to be true, and if phi is false then we do not make any statement about the psi, and therefore the whole statement is true. Only if the psi is true, only if the phi is true and the psi is false, then we would infer something false from something true, and this should not be the case, and therefore we have a false here. And if we look at this set view, then we have all assignments that are under which falsify phi are in the set of satisfying assignments of the implication, and all satisfying assignments of psi are in the set of satisfying assignments of the implication. Yeah, so when psi is false, then the implication is true. This is all the assignments outside of the circle of phi, And also if phi is true, therefore all assignments that satisfy psi are here in the set of satisfying assignments of the implication. Some example, if the atom it rains is true and the atom the street is wet is true, then the statement if it rains the street is wet is also true. Yeah? And with this we can infer, we can also use this to infer something. Yeah? If we just would know that it rains and we know this implication, if it rains the street is wet, has to hold, then from the knowledge it rains we can infer that the street is wet. And this is a very powerful inference mechanism in logic. This is called modus ponens. This comes from the semantics of the implication. Okay, then bottom implies A is always true because X falls on Quod libet. A implies A is also always true because either A is false, then the left hand side is false and everything is okay, or A is true, then the right hand side is true, and therefore the expression is true. Top implies phi is true if phi is true. Yeah. Okay, and then finally we have the equivalence. An equivalence is true if both subformulas have the same value. Also here we have some different notations, and the satisfying assignments are exactly those where phi and psi take the same truth value. So phi is equivalent to psi if both are 0 or if both are 1. Then we get a 1. If they're different, then we have zeros here. Hence the formula A is equivalent to A is always true. The formula A is equivalent to B is true if and only if A is true and B is true, or if A is false and B is false. And the formula top is equivalent to bottom is always false because these two truth constants can never take the same value by definition. And a very important observation we can make is that we can use one or two or multiple connectives to define other connectives. Yeah? When we look at this table here, we have two formulas, phi and psi, and let's construct the formula here, which is not phi and which is not phi and not psi. And I will not evaluate it slowly, but one can, when evaluating the different parts of this formula, and I will show you in the exercises how to do that, then we get that with this formula we exactly express the disjunction. With this formula here we exactly express the implication, and with this formula here we exactly express equivalence. Yeah? Although we did not use here a disjunction to describe the disjunction, here we did not use implication, and here we did not use the equivalence symbol. So we can express one formula or the meaning of one connective in terms of others. And this leads us to the notion of functional completeness. And let's us first think how many different functions or Boolean connectives, or how many functions we have that can be represented by the Boolean connectives. So if we have arity 0, then we have two possibilities. We have bottom or top. There is no argument. These are the two constants. If we have one operand, then we get 4 functions in total. One of them is the negation, the not, but it could also be identity. If we have an operator of arity 2, then we already get 16 functions, and if of arity n, we get 2 to the power of 2 to the power of n. So a function of arity n has 2 to the power of n different combinations of arguments. Yeah, so for example, if we have a binary connectives, we have 4 lines in the truth table. If we have an operator of arity 1, then we have 2 lines in the truth table, and yeah, then we have again a lot of possibilities how the concrete functions look like, and yeah, this formula here give the number of possibilities, and such a function maps the arguments either to 1 or to 0. Okay, and a set of functions is called functional complete for propositional logic if and only if it's possible to express all other functions with functions from this set. Yeah, and for example, we can express all other functions if we have negation and conjunction, or we can express all other functions when we have negation and disjunctions. Yeah, this is now with this function. I do not want to formally introduce it in much detail. Also here I could be more concise on that. I think for now this is enough, and later on we can look at how to formally write it down. But the point here is that if we have a subset of the connectives, we can express the other connectives, and therefore it's not necessary to consider all possibilities, but it's enough to consider just a subset. Okay, and yeah, as indicated before, we have 16 possibilities for the binary connectives, and here I have some other prominent connectives that I did not mention. Before we had just conjunction, disjunction, equivalence, and implication. What is also very important is the XOR, the exclusive OR, which is true if and only if the 2 immediate subformulas are different. Then we have the NAND, which is the negation of an AND. Yeah? So if at least one of the subformulas is false, then the formula is true, and only if both immediate subformulas are true, then the NAND of the 2 formulas is false. And similarly, we can define a NOR, and NAND and NOR are very interesting because they are functional complete on their own, and with them we can express any other Boolean function. We will also discuss this in the exercise class, or maybe you can play around with this and use this definition and see if you figure out how to express a negation or an AND or an OR with this, but we will also discuss this in the exercises. And as they are functional complete and they are quite good to realize in terms of hardware, they play an important role in building digital circuits like processors. Yeah? Here we have the definition. Okay, and now we can also write down the semantics of propositional logic like we did it for the CNF in a more descriptive way. And we do it as follows: given an assignment, and then we define the interpretation which maps a formula to a Boolean variable with respect to this assignment. If the formula is under consideration is top, then the value is always true. If the formula under consideration is bottom, formula evaluates to false. If we are considering an atom, then the value depends on this given assignment. If we have a negated formula, not phi, then this formula is true if and only if phi is false. And if we have a formula phi or psi, which is true, then this can only be the case if at least one of the immediate subformulas is true. And the question is now, what is about the other connective with this short definition? Yeah, and as I mentioned before, negation and disjunction together are functional complete. So with having these two, we can define the semantics of all other connectives as well, and we do not have to write it down explicitly. Yeah, and maybe you do not like this writing style here. We can also easily express this as a code by defining an evaluation function. We define an algorithm that evaluates a formula phi, and the algorithm returns value 1 if and only if phi is satisfiable. We proceed now as follows. First of all, we have to construct the assignment, which assigns every variable in the formula a truth value. So we pick one variable in the formula, and then we evaluate the formula by replacing this picked variable by one of the truth values, top and bottom, which we pick as well. Yeah, so we assign this value v to variable x. If this formula then evaluates to true, which we do by a recursive call, then we return true. Otherwise, we evaluate the formula which we obtained by replacing x by the negation of the value we have picked before. So we consider the other case, and if this is true, we return true. If it is false, we return false. Yeah? And if we do this recursive call, at some point the formula does not contain any variables anymore. We have replaced all variables by truth values, and then we can evaluate this formula, which does not contain variables. If the formula is simply top, we return 1. If it's bottom, we return false. So this is the base case. And now we do not have any variable. We just directly continue with the negation. If we have a formula not psi, then we return the value of psi and negate it. Yeah? So we evaluate the immediate subformula and negate the outcome. If we have a conjunction, then we have to evaluate the one immediate subformula, we have to evaluate the other immediate subformula, and then we return true if both of them are true. And similar, we do it for the disjunction. We evaluate the two immediate subformulas, and if one of them, at least one of them is true, we return true. Yeah, and that's basically the semantics of the propositional formulas. We call an assignment under which a formula evaluates to true a satisfying assignment, and we call an assignment under which a formula evaluates to false a falsifying assignment. A satisfying assignment is also called a model of a formula, and a falsifying assignment is also called a counter model. And if we have this formula here, x and y are not set, then not x, y, z is a counter model. We set x to false, then this conjunction is false, and we set z to true, then this not set is false, and therefore this formula evaluates to false under this assignment. And x, y, z is a model, and x, y, not z is another model. Yeah, this you can easily check with a truth table. And we call a formula satisfiable if and only if there exists an interpretation under which the formula evaluates to, if there exists an assignment under which the formula evaluates to true. We call a formula valid if it evaluates to true under all assignments. We call a formula refutable if there is an assignment under which it evaluates to false, and we call a formula unsatisfiable if there is no formula under which the formula evaluates to true. So if for all assignments the formula evaluates to false. We can check this with the Sat Solver Limbo. If you use the command line feature, so you do not use the web interface but the command line feature, as I will show in the exercises, you have to use the -s for satisfiability checking, and if you do not give an option, it will check validity. So it will check if all possible assignments are a model of the given formula. And yeah, you can also use, so Limbo can do satisfiability checking and validity checking. You can also check for unsatisfiability, and if it's refutable. If you check if a formula is satisfiable and it's unsatisfiable, then you will figure out with Limbo -s. If it's refutable, then it will check validity, and it gives you a counter model if it's refutable. So there is one model, one assignment given that is a counter model. But we will see this in the exercises in more detail. Okay, then a formula that is valid is a tautology. So a valid formula is a formula which has only for which all assignments are models, and this is called a tautology. An unsatisfiable formula is called a contradiction. Top is valid, bottom is unsatisfiable, A or not B, and not A or B is refutable. A counter model would be, for example, setting A to false and B to true. Then this clause here is falsified. A implies B is satisfiable. A is equivalent to not A is a contradiction. This can never be true because A can never have the same value as not A, and the formula which we had here before is not only refutable, but it's also satisfiable. Okay, and then we can relate the properties of propositional formula. A satisfiable formula is possibly valid, it's possibly refutable, but it's not unsatisfiable. Yeah, if I know that a formula is satisfiable, then it can be that it's valid, that all other assignments are models as well, but I know at least that there is one model of the formula. But it can also be refutable, so other assignments can be counter models, but it's definitely not unsatisfiable because of the satisfiability property. We know there is at least one model. A valid formula is always satisfiable, as all assignments are model. It's not refutable, and it's not unsatisfiable. A refutable formula, on the other hand, is possibly satisfiable, it's possibly unsatisfiable, but it's definitely not valid because we have at least one counter model because of the refutability property. And an unsatisfiable formula is refutable, it's not valid, and it's not satisfiable. Yeah, and here we have an example of a formula that is satisfiable but not valid. A is equivalent to B. For example, if we set A to true and B to true, the formula evaluates to true. But if we set A to true and B to false, then we have a counter model. A formula is satisfiable and refutable. We have also here A or B and not A or C, so we can find an assignment under which the formula evaluates to true, but we can also find a counter example. A formula that is valid and hence not refutable is top or something. As we have said before, as soon as one immediate subformula of a disjunction is true, then the whole thing is true, and top is always true, therefore this part is true. And then we have a formula that is not valid and refutable. We have bottom or B, and we can find an assignment that is a counter model when we set B to false, and therefore it's refutable, but in fact we could also make the formula true by setting B to true. Yeah, and these are very important properties, and this gives us the following connections between formulas. A formula phi is valid if and only not phi is unsatisfiable. Yeah. So if a formula is valid, it has no counter model. All assignments are models. And therefore the opposite of this formula, the negation of the formula, is unsatisfiable. Yeah, because every assignment is a model of phi, therefore not phi has no counter models, has no models, and therefore it's unsatisfiable. A formula phi is satisfiable if and only if not phi is not valid. Yeah, because then not phi has a counter model if it's not valid. Yeah, and this counter model of not phi is a model of phi. If two formulas phi and psi are equivalent, if and only if phi is equivalent to psi is a valid formula. So no matter how I set the values, the variables of phi, the value I get is the same value which I get when I set the variables of psi with the same assignment. Yeah. So we can express the equivalence check in terms of a validity check. And the formulas phi and psi are equivalent if and only if the negation of this equivalence check is unsatisfiable. This follows from the observation we have made here above. Yeah, and this brings us to the notion of semantic equivalences, which allows us to relate different formulas as we have just actually done. And this also gives us some important rewriting possibilities to modify a formula such that the value is preserved, but we get a simpler formula, and this might then simplify the solving. Okay, we call two formulas semantically equivalent if and only if for all interpretations they have the same value. So no matter which assignment I take and what value I get for the one formula under this assignment, I have to get the same value for the other formula as well. We write semantic equivalence with this arrow here, with the two lines. And this symbol is not a symbol we have in the language of propositional logic, but it's a meta symbol which we use to talk about formulas. Yeah, it allows us to relate to formulas. The nice thing is that we have something similar in the language of propositional logic, which we can use to express this property here. Yeah? Usually we somehow have to prove that two formulas are semantically equivalent to write it down. And when we have a formula phi and a formula psi, and the formula phi is equivalent to psi is a valid formula, then this means the two formulas are semantically equivalent. So this means we can express semantics by the means of syntactics. And it's not so hard to see that if we can show this validity of the formula here, then this also gives us the property of semantic equivalence. And the same holds in the other direction as well. Okay, and two formulas phi and psi are not equivalent. If this is the case, then we cross this symbol out simply. Yeah, and when I talk about equivalence and do not mention some qualifier, I do not say that semantically equivalent means, then I usually talk about semantic equivalence because this is the main kind of equivalence we are interested in. There are other kinds as well, but usually we mean the semantic equivalence. Yeah, here I have some example. A or not A is equivalent to B or not B because both formulas are tautologies, so no matter how I choose A, how I choose B, we always get true. Here I have a bit, maybe let's look at this example. A is equivalent to B is equivalent to C, is equivalent, semantically equivalent to A is equivalent to B, which is equivalent to C. And when you take a truth table, you can very easily show that both formulas, which we have on the left-hand side and on the right-hand side of this arrow with the double lines, are indeed equivalent. Okay, and to make it more structured, here I have some very prominent equivalences, which also are very important for solving formulas and which we already used a bit. You recall at the last lesson we said the order of a conjunction of the clauses in a CNF does not matter. Yeah, this is because phi and psi is semantically equivalent to psi and phi, and the same holds for disjunction. Yeah, so commutativity is such a property that we have. The same is for associativity, a very interesting property in this logic in the context of this Boolean domain is what we have here is an equivalence, a semantic equivalence called absorption. If we have a formula phi and then in parentheses phi or psi, then this is equivalent to phi. And we can also have a dual version of that. Phi or phi and psi is equivalent to phi. You can very easily figure out why this is the case when looking at the truth table. When phi, for example, is true, then the whole thing is true. Yeah, so it's enough to consider phi. If phi is false, then here this left-hand side is false, and also the conjunction, this inner conjunction is false, and therefore the whole formula is false, and this gives again the value of phi. Yeah, then we have distributivity. This you should also know from math. So if we have phi and psi or gamma, then we can distribute this phi inside and get phi and psi or phi and gamma. This is distributivity. Very important, the laws of De Morgan. If we have a formula not phi and psi, then this is the same as not phi or not psi. So we can shift the negation inside and have the negation symbol in front of the formula, and the Boolean operator here flips, so the conjunction becomes a disjunction, and we have the dual version here. If we have not phi or psi, this is equivalent to not phi and not psi. And these are the laws of De Morgan, and they play a very important role in order to transform a formula from an arbitrary structure into a CNF formula. Yeah, then we can rewrite equivalences in terms of implications, or even the implications we can somehow rewrite and omit. Yeah. We have used this already in the context of functional completeness when we wanted to indicate that one operator can be represented in terms of another operator, and what we implicitly there was to look for semantically equivalent representations. Yeah. Yeah, here is a representation of implication. So phi or psi is the same as not phi implies psi. Phi implies psi can also be written as not psi implies not phi. Yeah, then these rules of a complement, these we have already seen a lot. Phi and not phi is equivalent to bottom. Phi or not phi is equivalent to top. Yeah? And we also argued a lot why this is indeed the case. If we have double negation, then we can omit it. So not phi is the same as phi. And then, yeah, we have neutrality. Phi and top is the same as phi. Phi or bottom is the same as bottom. And then when we have phi or top is top, phi and bottom is bottom, not top is bottom, and not bottom is top. Yeah, and you might say, okay, oh, do I have to learn all these laws now by heart? I think they come quite natural, and if you understand them, then it's not so much to learn, but you should know them, as you know, for example, distributivity for multiplication and plus. Yeah? Otherwise, you cannot work with these expressions. And here it's the same, but if you think a bit about it and maybe play around it with the and do the truth tables, for example, or try to transform one into the other, then you will see that this these equivalences do not come very surprisingly, and they really help to solve the formulas. Yeah, in the exercise class, we will have a look at these equivalences in more detail and do some examples that you get more familiar with them. Okay, now we're almost at the end of the lecture. To conclude, I would like to show you a quick demo with the Limbo Solver, now with the full language and with validity checking. For this I have to switch my window. Okay, now we use the Limbo Solver with the full language it supports. So let's first start with a satisfiability check. So we ask, is there an assignment under which the given formula evaluates to true? Let's consider, for example, A implies B and not C or D. Okay, and let's see if this formula has a model. Therefore, we press run, and Limbo says yes, it's a satisfiable formula. If we set A to true and B to true and C to false and D to false, then the formula evaluates to true. Obviously, this is the case. We could now refine it and say, okay, we want to check if there is also a model where A is false. This I do by adding a constraint and not A. Yeah, so I, in addition, require that A is false. If I give this clause of size 1, then A should be false. And if I run it again, I get another model where A is set to false. Okay, now I maybe want to exclude that B is set to false. As I can do like that. If I run it now, if I want to exclude that B is set to false, I have to add and B. Yeah, then B is forced to be true, and indeed in this model B is set to true. Okay, now let's consider. Let's do something very odd. Let's add A may not be false, we have said before, and now we add A, no, before we said A should be false, and now we say also A should be true. If we run it now, then we have here not A, and therefore the formula is unsatisfiable. Okay, but let's remove it. So we have again our satisfiable formula. Now we could also check if the formula is valid. This means that we want to know if every assignment is a model, and this is not the case. And what we get now is a counter model, an assignment which says how to assign the variables such that the formula becomes false. Okay, and yeah, this is what we do with a validity check. If we consider this formula, A implies not A, then this should be A implies A, sorry, then this should be a valid formula, and indeed the output is this is a valid formula. Yeah, and now we can ask, is this equivalent to not A or B, not A or A, like that. So this is a way of rewriting the implication. Yeah, A implies A, and we wonder, or no, let's say A implies B is the same like not A or B. Yeah, that's a bit more interesting, because otherwise we just have this tautology there. Okay, and if we now run this, then the solver says, yep, this is a valid formula. A implies B always has the same value, we like not A or B. If I replace the or with an and, then the solver says, there is a counter model. The two formulas are not equivalent. This formula is not, because this formula is not valid, and we get a counter example. If we set A and B both to true, then the left-hand side is true, but the right-hand side is false. Yeah. And again, let's switch to satisfiability checking. If we type run, then this formula is satisfiable, obviously, because we cannot find an assignment that makes the left-hand side and the right-hand side true. But it's not the case, as we have seen before, for all possible assignments. Okay, as you have maybe noticed, there is a third option here. This is QBF Satisfiability Check. QBF is an extension of propositional logic with quantifiers, but this is not needed for this course. So, we will see them in a later course. Okay, that was it for today. Please join the exercise classes. There you will see a lot of more examples and practical tips, and also more Limbo demos. And yeah, thank you for watching.